So chapter 1 is a little bit about just a little introduction to chemistry. It also has some math review in there, which may be very helpful for some people. And again, at the end there, it talks a little bit about significant figures and things of that nature. So, and by the way, everybody sitting here is in section, just to make sure nobody's missing lab right now. Everybody sitting here is in section 31197, yes? And you have lab on Wednesday, right? Okay. Okay, so a little bit about chemistry. Chemistry obviously touches every aspect of our life. And really the main focus of chemistry and a lot of what we deal with is really the study of and composition of matter. And matter is really anything that has mass and occupies space. So matter is really anything that has mass and occupies space. That's pretty much everything if you think about it. A lot of what we look at in chemistry is how matter changes as a result of chemical reactions, also how matter changes as a result of physical changes. Very common sort of things that we look at is how matter changes from one state to the next. There are several states of matter that we come across. There is the solid state of matter. And in the solid state of matter, everybody is typically usually packed in there pretty tight to one another. There's not a lot of room for movement. They don't have a lot of energy. That's really why they are solid, right? They're rigid, like this countertop. We then also have the liquid state of matter. And in the liquid state of matter, everybody's still relatively in there pretty close to one another, but there is more room for movement. They have a little bit more energy. They're able to actually sort of pass each other. And that's why when we think about liquids, we think of them as being fluid, right? They pour and they have that liquid sort of state, if you will. The last state of matter, which is very common that we talk a lot about, is the gas state. And in the gas state of matter, pretty much everybody has 100% broken apart from one another. They're flying around in the container they're in. They're colliding with the walls of the container, which causes pressure that we associate with gases. So a lot of what we look at in chemistry is really these different states of matter, what's going on with these different states of matter, and also the transition as you go from one state to the next. So when we take something from the solid state to the liquid state, that's the process known as, when we take an ice cube out, it starts to melt. Yeah, it's the process of melting, right? So that is the process of melting. If we feel bad about our melted ice cube, we can take it from liquid back to solid by putting it in the, yeah, so that's the process of freezing, right? When we take something from liquid to solid. When we go from liquid to gas, that's the process of evaporation. Yeah, it's a process of evaporation, or sometimes vaporization is referred to. When we have a lot of gas that gets cooled down a lot, it then goes through the process of condensation as we go from gas back to liquid. There's also a process where we go from solid directly to gas, and we skip the whole liquid part of it, and that is the process known as sublimation. Like dry ice, perhaps you've seen dry ice before. That is sublimation. And there's also the process going from gas back to solid, and that is the process of deposition. Please no videotaping or pictures or anything like that. It is being recorded, so you could go watch it later. So the process going from gas back to solid, that is, again, the process of deposition, like you deposit stuff on there, also skipping the liquid phase. You don't see them too often anymore, like DVDs, CDs, how come they're shining up on top. That's how they get them shiny, to actually deposit metals up on them. So a lot of what we look at is sort of these different changes of phase and states. They also do require energy to do these things, which is another big aspect of chemistry that we look at. As we go from solid, say, to liquid to gas, do I need to put energy in to do that or take energy out? Energy actually needs to go in or be absorbed to do that. So if you take like the ice cube example, right, it picks up all the energy from the surroundings, it starts to melt. You take some liquid water, want to make some pasta for dinner, you put it on the stove and you put some fire underneath it, right? Gains all the energy from the fire and actually goes from liquid, right, and starts to boil, right? And you got gas that's basically happened. So those processes, as you go from solid to liquid to gas, involves energy being absorbed. That is sometimes referred to as a endothermic process. And then obviously going the sort of opposite way, going from gas to liquid to solid, we need to actually remove energy and let energy sort of escape. So energy is removed or released. So when you have gas molecules that are flying around really fast and moving all over the place, as they lose energy, what happens is they come in contact with other gas molecules. And frankly, they don't have enough energy to escape them anymore. And they kind of drop into the liquid phase. You continue to remove energy, like when you put your liquid water into the freezer, energy removes. And basically what will happen is they then will kind of lock into place and not be able to go anywhere else. When energy is released in a process, that is what is referred to as being an exothermic process. Any questions on that? Yeah.
So like how does that work? Are they an endothermic process and
there are certain processes, and we'll talk a little bit about it, I think, in a later chapter, but there's certain processes where there's kind of a net release of energy that occurs, which is an exothermic process. So that process or that reaction gives off. So for example, when you light a match, right, or a Bunsen burner, for example, right, you could feel heat, right? And that's the process of that reaction, which is a combustion reaction, giving off heat and energy to the surroundings, and you're picking it up. If you ever like a cold pack or something like that, right? Maybe they have ones where you can break it, right? And it becomes hot or cold, right? So when you do that, there's certain reactions when you kind of break those cold packs, the reaction actually absorbs energy. And what happens, it's endothermic for the reaction, because when you put it on your skin, all the heat and energy from your skin goes into the ice pack, right? And you start to feel cold, right? Opposite how a hot pack works, right? When you break it, that reaction releases all that heat and energy. And when you put the pad on it, your skin then collects all the heat and energy and you feel warm and that type of stuff. So there's lots of processes that overall sort of give off energy or absorb energy just as a result of that reaction taking place. And there's certain times where you have to sort of add some energy to make something occur, or maybe has to remove some energy to slow down a reaction or something like that. Other questions? Okay. All right, so as I mentioned, matter is basically the stuff that pretty much makes up everything. So it really is anything that has mass and occupied space. Talk a little bit about some of these things here. Let's get through some of these things. We'll talk a little bit about the scientific method. And again, this is sort of like a little overview chapter, and we'll get into some more specifics in later chapters. But the scientific method is one where it really does involve sort of observations. And that's usually how sort of the process starts. You observe something that occurs. And when you observe something that occurs, it makes you think, well, why did that happen, basically? So really, it all starts with an observation. And really, the next step is to come up with a hypothesis. And a hypothesis is really a testable sort of explanation as to why you think something occurred. And a good hypothesis is sort of a chemistry relationship, or a science relationship is one where you could then go do some type of experiment to test your hypothesis. So maybe you observe something happen, you come up with an idea as to why you think that maybe have occurred. And then that leads into really experiments. And You do these experiments to either maybe prove your hypothesis or disprove your hypothesis. A lot of times what happens when you do the experiments is you make more observations. You maybe even observe something that you didn't see maybe in the first place, which leads to more questions, more observations, more hypotheses, and more experiments. It can be sort of a vicious circle, if you will, from observations to experiments to hypothesis, or sort of revising hypothesis. At some point, you usually come up with one of two things. You usually come up with a theory or a law. And there is a difference between these two things. So a theory is sort of a tentative explanation of what is going on. And a theory may not always be 100% correct in all aspects of it, but it's sort of an idea of sort of what is going on. There's lots of theories in chemistry where over the years, it's like, well, not so correct anymore. So for example, Bohr's model of the atom. Bohr's model of the atom is sort of a nice planetary model where the electrons travel in pretty circles around the nucleus, and that's really not what happens. So it doesn't hold up over the time. There's other experiments that come by and go, no, I don't think that's really good. It works really well for hydrogen, but once you get past hydrogen, it doesn't really hold up. So a theory may not always be perfect in every aspect. It may be found to be maybe later down the road, not so correct in all aspects. Some parts of it may be correct. Other parts may not be correct. Like Dalton's atomic theory, there's a couple of parts that are correct and there's some parts that are not correct. And that's basically what a theory is, sort of a tentative sort of explanation, not set in stone, can be sort of revisited through further experimentation. A law, on the other hand, is something that no matter what happens, it pretty much always happens that way. So if you have something like the conservation of mass, which means in a chemical reaction, we don't lose any mass. So whatever we start with and whatever we end with is basically the same thing. That's one you may be familiar with, and we'll talk about when we get to another chapter, like when we balance an equation. So for example, if we started with like 4 carbons, we'll end up with 4 carbons at the end of the reaction. They may be in different things, but we won't lose any carbons along the way. And that's the conservation of mass, because in a chemical reaction, really the only thing that occurs is we break bonds and make new bonds. So we don't lose any elements along the way. Everybody maintains. And that always happens no matter what. And that's sort of a conservation of, that's basically a law. Conservation of energy is another one. We don't make or lose energy, but energy can be moved from one place to the next. So there's sort of a perfect sort of exchange of energy that occurs. And like the example of the hot pad or the cold thing that we were just talking about, when you do that reaction and say that it releases that energy, it has to go somewhere. And where it goes, for example, again, is your hand. So the amount of energy that reaction releases would be the exact same amount of energy that your hand picks up, basically. So there's like a perfect exchange of energy. And that's the idea of something like the law of conservation of energy. We don't lose it. We don't make more. There's just this nice, perfect exchange. So laws, on the other hand, are things that you do it any which way you do it. It always occurs the exact same way. Theories are, again, things that can be sort of revised over years, may not be perfect in all aspects, and are maybe good in most parts and not always all the parts of it. So here's sort of a visual of the scientific method. Again, observations leading to hypotheses, leading to experiments, making more observations leading to more hypotheses. And again, at some point, hopefully you get to a theory or some type of law that comes out of that. Any questions on that there? Like the cat. All right. All right. So let's talk a little bit about math, which is a really important part of this class. This class is sort of 2 parts, if you will, in terms of math. There's math, there's formulas, there's things you have to solve. So like chapters 1 through 9-ish, 10-ish maybe. It's all about calculator, doing formulas, or a lot of it, getting numbers and doing calculations of math. Once we get into organic chemistry, the later chapters, and also lipids, proteins, biochemistry, there's pretty much no calculations. It's all memorization. So some people really like the first half because they like calculations. Some people can't wait for the second half where they put their calculator away and don't have to pick it up, you know, and then it's more memorization and stuff like that. So there really is sort of two parts to this class. First part being more math-based, second part being really more sort of memorization and naming and then that type of base. Frankly, you don't pick up your calculator until you take exam 3 because there's like chapter 10 on it that has some calculations, and other than that. So just a reminder, some basic math skills. And again, chapter 1 kind of goes over some of these things. You know, we want to make sure we understand, you know, we have our thousands place, our hundreds place, our tens and our ones place when we look at a number, so we understand it. Most importantly as well in chemistry, when we take any type of measurement, you always want to make sure you have a number and units associated with it, as we'll talk about in chapter 2. But really, if you just write something like 200, there's really no reference to that, right? That could be 200 apples, that could be 200 pennies. There's no really meaning for what that number represents. So really in chemistry, definitely you always want to make sure you use those units. Maybe it's grams or something like that, but you want to make sure you always have numbers and units, and we're very commonly should always put those things down. So sometimes people just kind of forget the units, but it's a really important aspect of the number that helps people understand sort of what's going on. We also have decimal places, which is important. We have our ones place, then we have our tens, hundreds, and thousands place as we come through here. So obviously we have our numbers here. So we have our tens place, our ones place, our tenths, and our hundredth place as we come through. Positive and negative numbers, we do come across both. So a reminder that a positive number, we typically do not write the positive sign like we see there, but definitely if it is a negative number, you should include the negative sign. So negative should always be included. By the way, speaking of calculators, most calculators have an actual negative button. And most calculators, it looks something like this, a plus negative, or it has kind of something like this. You want to make sure if you are putting a number into your calculator that is negative, that you do use the negative button. You do not want to use the subtract button, which is a common sort of mistake that people will make. They'll use sort of the subtract button. You want to make sure that you use one of those negative buttons. If we multiply two negatives, right, it becomes positive, right? So two negatives become positive. If we take a negative times a positive, we end up with a negative number, right? If we add a positive number and a negative number, that's essentially like subtracting, right? So that's basically 3 minus 2, which is 1 in this case. And again, obviously, if we were adding two negative numbers, we just basically add them and then obviously keep the negative part of it as well. All right. When we divide, same deal. If we divide two positive numbers, we end up with a positive. If we divide two negative numbers, we end up with a positive number. And if we divide a negative and a positive number, we end up with a negative number, right? So again, it's important to make sure that you understand these basic sort of calculations. All right. So we did that. So some important buttons on your calculator as we go through this, as I just mentioned, your positive and negative button, as you can see, that is this guy right here, or your this button here. And as we'll talk about here in just a second, which is scientific notation, there's actually an exponent buttons on most people's calculators, either an EE button, an EXP button. And if you have sort of a newer calculator, you will have a times 10 to the n button. Those are some important buttons to identify for your particular calculator. Obviously, you want to make sure you put it in. When we do problems, by the way, and it's a very common calculator error that people do. So say, for example, we were taking 55, and then we're going to multiply it by 32. and 32, and then we got like 14 and 16 we're dividing. So if you have something set up like this, mathematically what we would be doing is everything on top we would be multiplying, and then we would be coming back on the bottom basically and dividing by everything that's on the bottom. And what happens sometimes when people in calculators and they're doing some type of calculation is they oftentimes want to put everything in all once. Just like I want to like lay up everything onto my calculator. And that's perfectly okay to do if you know how to properly do it and you use parentheses. In my experience, most people don't do it correctly. Most people don't do the parentheses correctly and stuff like that. And they end up with the wrong answer, because if you don't put the parentheses in your calculator, although we think of calculators as being really smart, they're really dumb sometimes how they're programmed. So if you don't put it in correctly, you'll get it wrong. So if you ever have some type of problem like this where you're doing a bunch of multiplications in a row, and then you got to come back and divide it by a bunch of numbers on the bottom, it's really important just to, you can take as many numbers up on top as you want and multiply, but you just want to hit equals when you're done with it all. And then what you want to do is come back and divide by the first number, hit equals, divide by the second number, hit equals, and you will always get the right answer if you kind of do it that way instead of trying to put everything in at once. So for example, this, what I wrote up here, I would punch into my calculator 55, I would hit the multiplication button, 32, I would hit the multiplication button, 32, and then I would hit equals. That takes care of all the multiplication we're doing up here on top. Then I would actually hit the divide button and hit 14 and then hit equals. Then I would hit the divide button again, hit 16 and then hit equals, and you're guaranteed to get the right answer. If you try to again put it all in at once, there's probably a good chance you will not get the right answer when you get there. Any questions on that? So it's really important to make sure you understand how to punch things into your calculators. And that's why it's important to bring your calculator with you to class so that you can actually punch it in, and that it is the calculator you're going to use on an exam or quiz. I will usually go through as we punch things in, like, hey, this is how you punch it in, to make sure you know how to hopefully do it correctly. So again, there's a lot of that here in chapter 1 that will kind of, if you want to go through it, just to remind yourself. Another very common thing that we do in chemistry is we oftentimes are given numbers as percentages, like, hey, this is 52% by mass, say sodium chloride or something like that. Say 52% by mass sodium chloride solution. So a lot of times we want to use these percentages as like a conversion factor. So really the best way to sort of convert a percentage into a sort of a usable number is to assume that you have 100 of it, right? And, you know, if you got like 80 on the exam, you probably got 80 points out of 100, right? So it keeps the numbers the same. So for example, if I were to kind of convert this into a conversion factor that I could use, this would be something like, for example, 52 grams of sodium chloride in 100 grams of solution. So that is basically 52%, but it gives us two values that we could use in a calculation. We also could flip it around and do like 100 grams of solution over 52 grams of sodium chloride. So a lot of times we're given things in percentages and we need to kind of use them to do some type of calculation. And then the easiest way to do it is just assume that you have 100 of whatever it is, and basically the numbers stay the same. You could assume whatever you want, but if you had 200 grams, then you got to multiply it by 2 and the numbers start changing. So it's just much easier. So if we want to calculate a percentage like here, 325 milligrams out of 545 is 59.6% aspirin in that case. So you basically divide it times by 100 is how you would calculate a percentage if you needed it. If I had 5 red balls out of 100 balls, that means I have 5% red balls. And here, if I have 50 green balls out of 100, I got 50% green balls. Again, here, 50 divided by 100 and times it by 100% will give me my 50%. All right. Now, we don't do too much, I would say, straight algebra, but we do, in a sense, have a lot of formulas that we do need to be able to properly rearrange in chemistry. So a reminder that the equal sign basically means is if you want to move something to the other side of the equal sign, you have to do the opposite operation to do that. So what do I mean by that? Well, here I want to move the 8 to the other side. I'm adding it, so I need to do the opposite to do that. The opposite is subtracting it from both sides. So again, to move the guy to the other side, you got to do the opposite of what's there. Those guys go away. That gives me 2x equals like 6. Now I want to get x by itself. When I look at 2x, that's basically 2 times x, right? So to get the 2 to the other side, opposite of multiplying is dividing, right? So I got to take the 2 to the other side. Those guys go away, gives me x is equal to 3. So we do have a lot of formulas. I would say definitely when we get into the gas chapter, there's a bunch of different gas formulas that you have to rearrange. And in general, basically, anytime you sort of move anything to the other side, if it's just variables, there's no like numbers. But if you move something to the other side of the equal side, it ends up in the opposite spot of where it started, basically. And that's basically what happens. So for example, if we had something like what we see here, P1 V1 equals P2 V2, this is actually a gas law. This is Boyle's law. Although they are not technically written as fractions, they basically are a fraction. They're both basically over 1, which means the P1 V1's up on top, the P2 V2's up on the top. So if I wanted to solve for V2 by itself, basically I need to take P2 and move it to the other side. So it's on the top on the right. When it goes to the other side, it goes to the opposite location, and it becomes P1 V1 P2 is equal to V2. So whenever you move anything across the equal sign, which we do a lot in sort of formula, especially in gas laws here, and they're all sort of variables, letters and stuff like that, opposite locations. So for example, if I had V1 T1 equals V2 T2, and I wanted to solve for V1, what would it be? Well, using the same logic here, basically to get V1 by itself, I have to move the T1, right? T1's on the bottom, which means when it moves over, it will end up on top, yeah? So V1 would equal V2 T1 T2, right? All we did is basically move the guy to the opposite location. So whenever you go across the equal sign, basically they will move into opposite locations. Mind you, if you are solving for something, you always want that guy to be on top by itself. So for example, if we had P1 T1 equals P2 T2, and let's say I wanted to solve for T2, right? And I want to actually solve for it. Right now, T2 is on the bottom. I need to get it to the top by itself, right? Which means I need to move it to the other side. So it should end up where? Should end up on top. So that would give me, if I just rewrote everything, T2 P1 T1 is equal to P2, right? Now what I need to do is keep this guy on top and move everybody else to the other side, right? So the P1 would end up where? P1 would end up on the bottom. The T1 would end up on top. And that would give me T2 is equal to P2 T1 P1. So again, you sometimes need to solve for some of these things, and we'll do more of this in later chapters, obviously. But there are formulas that you will need to rearrange. And the thing to remember, especially with the equal sign, is basically opposites as you move it across the equal sign. They end up in opposite locations. Yeah. It is. So in the first case, you know, if I was solving for P1 in this case, all I have to do is move T1 to the other side. I'm done. But you can never solve, for example, a very common mistake people will make is they're asked to do like solve for T2 like we were doing in this particular one. And what they'll do is, you know, they're solving for this. They'll go, okay, I'll just move this down this way. So that gives me P1, T1, P2 is equal to, is that really T2 on that side? That is actually 1 over T2, yeah? So that's actually not what you're looking for because it's 1 over T2. It's actually the inverse. You got to flip everybody back around to get it to the right one. So if you are solving for something, you know, you got to basically get it to the one side of the equal sign or the other, basically on top. And then you got to get everybody else to the other side. So sometimes it does have a lot of moves that she has to make, and sometimes it's just like one move to get everybody to the right side. Any questions on that? And again, we'll do more examples, obviously, when we go through different chapters and rearranging. But it is an important aspect of doing well in chemistry, is to be able to rearrange formulas, because it's really important, because if you don't know how to do it correctly, you will divide when you should multiply, right? Multiply when you should divide. So you'll be doing the wrong math and you'll get the wrong answer. So, you know, if that is an issue for you, you do want to take some time as we go through the different sort of chapters and the different formats, just to make sure you take some time to know how to properly sort of rearrange the formula so that you can solve for them. We're not going to do a lot of graphs in here, but if you want to read about it, you can. More importantly, actually, chapter 1, probably the most important thing, one of the most important things, if not the most, is scientific notation. We do come across scientific notation a lot in chemistry. If you're not familiar with what scientific notation is, it has a general formula of n times 10 to the n. And this first one is a number between 1 and 10. That means it can't be less than 1 and it can't be 10 or higher. So it's got to be a number between 1 and 10. So it's either got to be a 9 or it's got to be a 1 point something or 9 point something. It can't be 10 point something. It can't be 100 point something. Times 10 to the little n, which may be positive or negative number, depending on really which way you need to move the decimal point to get to a number between 1 and 10. We use scientific notation a lot because we have really big numbers that have lots of zeros, and we have really small numbers that have lots of zeros. You know, if you had something like Avogadro's number, which is like 6022000, I don't know how many zeros there are, but there's a lot of zeros. And clearly, if you kept that number like that and you want to kind of go on and do some more calculations, you're probably going to mess up and lose some zeros along the way. And same thing if we had a really small number that had a bunch of zeros to begin with, you may lose those. So we do use scientific notation to handle large numbers and small numbers. To convert something into scientific notation, you simply just move the decimal. So if you had 325, although there's not a decimal written, we assume it's here. And if I move it one place, that is now 32.5, which is not between 1 and 10. So I got to go one more place, and that is now 3.25, which is a number between 1 and 10. So this would be 3.25 times 10 to the 2. 2 because I had to move the decimal place 2 places to get to a number between 1 and 10. Positive because it's a large number. So anything that's sort of a large number or over 1 will have a positive exponent, or you move the decimal place to the left. If I had something like 0.00032556, the decimal points here, I got to go one place. That is not between 1 and 10. That's not between 1 and 10. That's not between 1 and 10. Finally, when I get to here, that is now going to be a number between 1 and 10. That would be 3.256 times 10 to the, moved it 1, 2, 3, 4 places, -4. Negative because it's a small number and I had to move the decimal place to the right. So it's important to know how to write scientific notation. Question on that there. So again, always a number between 1 and 10 to begin with. And again, this number may be something that is positive or negative, depending on which way. Now, if you do have something that is written in scientific notation and you want to turn it into a decimal form, you do the opposite. So 2 means here I'm going to move the decimal place 2 places. And because it is a positive one, I need to make it a larger number. We're going to go 1 and 2 and add a 0 to it. And we will end up with 150 as converting this into decimal form. Again, if you had something like 1.35 times 10 to the -3, the negative means it's going to be a small number, and to get a small number, we would go to the left to 3 places, and we would put our zeros in there. So we would end up with too many zeros there. 0.00135. And again, 1, 2, 3 would be the proper there. So it does depend on which way you're moving the decimal, but typically speaking, a good way to remember it is if it's a sort of larger number, it will have a positive exponent. If it has a smaller number, it has a negative exponent. Question on how to write scientific notation. So it's really important to know how to do it. Do you have to give every answer in scientific notation? The answer is no, unless it says to do so. We'll talk about in chapter 2, but you do need to give answers to the proper number of significant figures. And sometimes the only way to give the answer to the proper number of significant figures is to write it in scientific notation. When we do write a number in scientific notation, all the numbers here before the times 10 part are significant figures. So this number would have 3 significant figures based on the way it's written. The nice part about scientific notation is if you wanted just 2 significant figures, all you have to do is just write it like this. And now this would have 2 significant figures. So because you could kind of control how many significant figures, and we'll talk more about this in chapter 2, scientific notation is really helpful. And again, sometimes the only way to get the answer to the proper number of digits. More importantly than actually writing scientific notation is to actually know how to use your calculator in scientific notation. So let's focus on that to end this talk here about it. Let's find somewhere to write. So as I mentioned before, on everybody's calculator, there should be 1 of 3 buttons. That is actually your exponent button. That is the EE button. That is the EXP button. And again, if you have kind of a newer calculator, they're usually like 2-toned, like white and blue or something like that. They usually might have this button. And if they have that button, they typically will also have like a little dial on it. It looks something like that. So if you have this calculator button or that calculator, we'll talk about what you should do in a second. If you have these buttons here, we'll talk about what to do. But these are the proper buttons that you should use when you want to put a number into your calculator in scientific notation. Now, your calculator, does not always give you the answer in scientific notation. It does not give you the correct sig figs. It just gives you numbers. Now, if you have a program to give it to you in scientific notation, it will. But if you don't, most people don't. It may not give it to you, obviously, in scientific notation. So for example, if we wanted to put into our calculator this number 6.25 times 10 to the minus 14. The proper way to punch this number that's in scientific notation into your calculator is to do this. You would type 6.25. You then would actually hit your exponent button. So either the EE button, the EXP button. When you do that on most calculators, it will do this. It will go 6.25 and maybe put an E. It may go 6.25 and pop up a couple of zeros. Maybe it may even say times 10 on the bottom, really small, but it will pop up one of those 2 things when you hit those button. So when you hit the EE button or EXP button, that's typically what you would do. When you hit that EE button, that represents this part of the number. It represents the times 10 part. So when you hit that button, it represents the times 10 part of the number. That means that when you type a number in scientific notation, you should not hit the multiplication button. You should not hit like the second log button or inverse log button. You just need to hit that button there. And then the next thing we have is actually negative 14 is our exponent. So we want to make sure we use our negative button. So either the positive and negative or that like negative with the parentheses. When you do that, it will make this a negative. It will also put a negative here on if you have that display. And then what's left is 14. And when you do that, it will put a 14 here. It will turn this into a 14. And that is the proper way to actually punch a number in scientific notation into your calculator. If you have a positive exponent like 3.5 times 10 to the 2, you would type 3.5. You would hit your exponent button. And since it is positive 2, you would just hit 2. And that again would give you something that looks like this, 3.5 e to the 2, or 3.5, probably something that looks like that. So those are the proper ways to punch it in. If you have either the E button or the EXP button, you 100% want to make sure that you use those buttons when you're punching it in. If you do have this calculator here that has this button and the circle, You just have to do a couple of things because your calculator is programmed, well, wrong, but your programmed wrong. So you actually have to put parentheses around each number that's in scientific notation. So if you were going to do this number here, and you have this calculator, kind of a two-tone calculator, you actually need to go a parentheses, and then you need to do a 6.25, and then you need to hit your exponent button, which looks like this. And on your calculator, it will look like this. You'll have a parentheses, a 6.25. It will go times 10, and you'll have a little blinking cursor up there on top of the 10. At that point, you then could hit your negative button and 14. And what will happen is it will turn it into 6.25 times 10 to the negative 14. And now you still have your little blinker blinking next to the 14 up on top. That is where the wheel comes into play. You need to hit this button right here on the wheel. That will bring your cursor back down so you can close the parentheses correctly. And you want to close the parentheses at that point. And that's what you have to do if you have sort of that calculator. Not a big deal. You just got to kind of do some extra parentheses and stuff like that. And it's usually, again, the kind of the two-tone ones that have that button and that little wheel. You absolutely do not want to use the log button to do scientific notation. You don't want to use the multiplication button to do scientific notation.
For example, like the calculator gave you 3.5 E2, so then is that what you would write?
No, so this would be, for example, how you would want to punch. So let's say you were given two numbers or in scientific notation, and let's say maybe you need to multiply it or divide it. This is the proper way to actually punch the number into your calculator to enter it correctly. Now, for example, let's do a couple so you could try if you have a calculator. It's just let's do 6.2 times 10 to the minus 11, and let's divide it by 3.7 times 10 to the 22. Let's see what you get. And let's also do 4.15 times 10 to the 6. And let's multiply it by 7.7 times 10 to the minus 12. All right, so punch those in using your exponent button, see what you come up with. I'll do it as well because I just made it up. So let's take a look. And again, let's go through how to properly punch these in. So this would be, to answer your question, sort of a question like you might have where you have a couple of these numbers. And the key is to be able to punch it into your calculator sort of correctly. So we'll take the top one here. And if I were to punch this in, I would start with the 6.2. I then would hit my exponent button. Remember, that represents the times 10 part. I would then hit my negative button, and I would hit 11, and then I would hit divide. And again, that would most likely put something like 6.2 e negative 11, or it may go 6.2 times 10 to the negative 11 is how it will kind of display on your calculator. The next thing, we want to put this number in scientific notation as well. So we would go with 3.7. Once again, we're going to do our exponent button, which will take care of this part of the number. And the rest of it's a 22. So that will give us divided by 3.7 E22, or it may do 3.7 times 10 to the 22. We then want to hit equals in this case, yes. So if we do that here, 6.2, see how we did with my made up numbers, negative 11 divided by 3.7 exponent 22. All right, so we end up with a number with a lot of numbers. So I'm just going to round it, but you do end up with something like 1.6756. And then you don't want to forget all the way to the right on most people's calculator, there is a times 10 to the minus 33 part. Really, it will end up being something like 1.7 times 10 to the minus 33. So to answer the second part of your question, this is the proper way to record an answer in scientific notation. Now, if your calculator gave you something like, 1.6756 E minus 33, That is not the right way to report an answer in scientific notation. You should never write the E when you're given an answer. You should always convert it into the times 10 part when you're given it and stuff like that. Now, if you got an answer and you're not punching it in correctly, typically what will happen is this part of the number will be okay, but this part will be slightly off. And that's usually a very big indication that you're not punching it in correctly into your calculator. So if you see like that little exponent part's off a little bit, but the first part looks pretty good, is probably how you're punching into your calculator. Yeah. Yeah, so if you got e to the 36, again, it's probably the way it's maybe punched into that calculator. Yeah. So if we did the second one, we would do 4.15. We would hit our exponent button, which again would represent this part of the number. That's a positive 6, so we would put 6. We then would hit the multiplication button. We then would put 7.7, once again, exponent button, which represents this part of the number. This is a negative 12, so we want our negative button and 12, and then hit equals. And if you do that, you will end up with 4.15 exponent 6 times 7.7 exponent button negative 12. And this is actually going to give you a number like this, 0.000031955. Now, again, mine did not give it to me in scientific notation. If I want to turn this into scientific notation, my decimal point would go 1, 2, 3, 4, 5 places. And we would end up with something maybe like 3 point, and we'll round it to 2 times 10 to, what did I say there? 1, 2, 3, 4, 5, negative 5. Yeah. So that again is a key. It won't always give it to you in the scientific notation. It won't always give it to you the proper number significant figures. In chapter 2, obviously, we'll talk about how to figure out how far you should take the answers, but those are important things to keep in mind. So really important, probably the major take home for chapter 1 is how to punch your things into scientific notation in your calculator, how to write it, obviously, but more importantly as well, how to properly do it. If you're not sure or you have that other button, you do the same thing, except that again, you just need to put the parentheses around all those numbers and you'll be okay. If you're not sure where your exponent button is or how to use it, come find me at some point. I'll be happy to show it to you. Any questions on that? Yeah, that pretty much wraps up chapter 1.